Welcome to our learning video about price differentiation. With over 70,000 people taking public transportation in St. Gallen every day, there's a high need for the Transport Association St. Gallen to understand their customers' willingness to pay in order to maximize revenue and best meet the demands of riders. In this study, we identify key segments and prices to calculate the optimal pricing strategy. Therefore, we have conducted a survey among 50 students, which use the bus on a regular basis. We asked them how much they were willing to pay for a bus ride in the morning from 6 to 9 a.m., during the day from 9 to 4, in the evening from 4 to 9 p.m., and during the night from 9 p.m. till 6 a.m. We calculated the average willingness to pay for every person. In our first pricing model, we are looking for the optimal single price. Therefore, we sort the average willingness to pay from high to low and calculate the sample demand using the count-if function. In order to determine the overall demand, we use the capacity of one of the buses which are used in St. Gallen, the Hess Doppelgelenk trolley, which can transport 156 people. Using the overall demand and the corresponding prices, we plot the demand curve and add a linear trend line. Since we are using real-world, normally distributed data, as we can see here in this histogram, the linear trend line does not represent the demand well. Therefore, we use a fifth-degree polynomial instead, which approximates the demand curve much better. Using the equation, we can calculate the revenue for some possible price points. The color coding gives us a hint where the optimal price lies. Using the Excel solver, we can get the best price precisely, 2 francs and 1 Rappen. Now we want to improve the model by using differentiation. In the bus, we see that there are 52 seats and 104 places for standing. So we decided to introduce a pricing system which differentiates between the high class, those sitting, and the low class, those standing. In our first analysis, we identify 250 francs as the optimal price for the high class. However, with this price, 87 people would want to sit in the bus. This would require more seats than available in the bus. Therefore, we need to introduce the number of seats and the number of standing places as a capacity restriction to our model. We use the Excel solver to calculate the optimum prices for the 2 classes with restriction and get this result.
In our survey, we found out that the willingness to pay depends a lot on the time of the day. For example, the respondents want to pay more for getting home safely in the night compared with during the day. We believe this should be reflected in our pricing model. In order to do so, we separately looked at the willingness to pay for the morning, the day, the evening, and the night. We used the same procedure every time. We sorted the values, calculated the overall demand, and chose the fifth polynomial as our best-fitting trend line because of the normal distribution. Then we calculated the optimal price for the classes using the equation and the Excel solver while keeping the capacity restriction in mind. After repeating this for every time of day, we gathered the results in this table. Now it's time to compare our new model, which differentiates between 2 classes and the time of day, to our previous model and the actual prices in use by the Transport Association. For the comparison, we take the revenue per bus, which we have calculated in the steps before, and multiply them by the number of times the bus line 5 goes from Roodmond to Riethusli every day. For the current model of the Transport Association St. Gallen, we take the tariff for 2.6 francs on the day and 7.6 francs in the night. The model, which differentiates both the classes as well as the time of day, generates the most revenue, followed by the simple classing and our single price. Since, according to our demand curves, the current prices are too high, the revenue is lower than with our single prices.
Now we asked ourselves the questions. Are the demand curves for the various time frames significantly different from one another? To answer this question, we conducted a one-way analysis of variance, or ANOVA, using the data analysis add-in in Excel. The p-value of the ANOVA is below the level of significance, which means that there is a significant difference between some of the times of the day. However, from the ANOVA alone, we don't know which times are different from one another. To find out the details, we conduct post hoc t-tests. Since the risk for false positive results is higher when doing multiple t-tests, we correct the significance level by the Bonferroni factor, which means that we divide the significance level by the number of comparisons. This analysis shows us that there is a notable difference between all groups, except between the demand curve in the morning and the evening. Therefore, we cannot propose different prices for the morning and the evening.
Because of this, we calculated a new demand curve which combines the demand in the morning and the evening. We proceed as before and call the new prices the rush hour prices. We add the newly obtained prices to our comparison and observe that our final model generates a revenue which is 93% higher than with the current pricing strategy.
Now we can propose the new pricing model to the Transport Association St. Gallen and help them enhance their service.